So, welcome back student to this introduction to nonlinear optics and its application course. So, in this particular course for last few classes we learned the basic optics, which is very important because this is the building block of nonlinear optics. So, we start studying about the optics in an isotropic system. Optics means specially the light propagation. So, we will continue this discussion. So, let us go back to these slides. So, electromagnetic wave propagation in anisotropic media, it is continued. So, this was our starting point. In anisotropic system, the relationship between D, E, S and K in general is like this, that E and D are not parallel. So, that is why S and K are not parallel, but D and K will be perpendicular and E and S will be perpendicular. There is an angle between vector K and S, we call this angle is a Markov angle. We will calculate the amount of angle in terms of the refractive index along different directions. So, that is the process we are doing. So, this we have already explained in last class, and then we find these three equations, and these three equations are the relationship between the Kx, Ky, Kz with Ex, Ey, Ez. From directly Maxwell's equation we find out these three equations, and now we try to solve these three equations under different condition. So, in general if I launch E k vector in arbitrary direction, then these three equations will be simultaneously there. So, after that what we did in our last class, we put some kind of condition. So, the condition here is this. So, let me explain once again. So, these are the three equations. These are the three equations that we have derived. So, these are the three equations that we have already derived. So, these three equations are now put under some condition, and the condition is here. I show the same figure that we have done in the previous class, that if I put my k in such a way that it is along z direction. So, now my k is in z direction. If that is the case, then the vector, unit vector associated with, or the direction cosine associated with k vector is now rho x, rho y, rho z, and they are having value 0, 0, 1, because I am launching k in z direction. If that is the case, then in this mother equation, these three fundamental equations, I will going to put the value rho x, rho y and rho z, which is 0, 0, 1. Once I put rho x and rho y 0, my first equation will be, this term will vanish, this term will vanish, and rho x, this term will also vanish. We will have E x multiplied by k x n square minus 1, and here it is. This is my first equation under the condition rho x equal to 0, rho y equal to 0 and rho z equal to 1. Next, I will do the same thing in the next equation. If I put rho x equal to 0, rho y equal to 0, then this term will not be here, this term again will not be here, because this is multiplied by rho x, which is 0, but here rho y is again 0, and I will have my second equation, and the second equation is E y multiplied by k y by n square minus 1 is equal to 0. This is the second equation under the condition that E is launched, and finally we have other equations. So, rho x, rho z will be 0, this will be 0. Now, here rho z is equal to 1. So, 1 plus and 1 minus will cancel out. So, I will eventually have this equation. These equations suggest that when I launch my k vector in this direction, z direction, there will be no z component of the electric field. That means, my electric field has to be in the plane of x y. So, x y will be the plane which is perpendicular to the k. So, E vector should be in that plane, because E z, from here one solution we can have, from these three equation one solution we can have, and this solution here we can able to figure out very easily that it has to be 0, because kz is not equal to 0 and n square is not equal to 0. Kz is related to refractive index, kz is equal to n of z square of that. So, it is related to refractive index. So, it will never be 0. Nz means that the refractive index along z direction. So, it will never be 0, refractive index will never be 0, and if this is the case, then Ez has to be 0. That means, there will be no z component of the E. So, E has to be in x and y direct along this plane of x and y. So, the solution 1, as I mentioned in the last class, the solution 1 may be one solution is along, if I put E along y direction only, that means Ex component is there, Ex component is the only component that is here. So, Ex component is the only component. Okay, this is now another slide. Okay, this is the previous slide. So, solution 2 here is, one solution is Ex equal to 0, another solution is Ex equal to 0 and Ey is not equal to 0. If Ex is 0, but Ey is not equal to 0. If Ey is not equal to 0, then I will have a solution here, and in this case polarization will remain constant. That is one issue. Second thing is that from this equation, if I write Ey multiplied by ky by n square minus 1, that was my equation, and I am saying that Ey is not equal to 0, that essentially means that ky by n square minus 1 has to be 0. If ky by n square minus 1 is 0, that means ky is equal to n square. That means n, the refractive index along y direction is ky. In the previous case, we find the refractive index along y direction is kx root over of that. So, here one important thing one should note, that the refractive index experienced by the electric field is different in y direction when it is polarized along y direction and when it is polarized along x direction. So, that is the important thing here, because the refractive index may not be same in y direction and x direction, and that is the property of the isotropic system. That is indeed the property of the isotropic system. Now, we will come back to solution 3, that is rather more important, and that is, I am now launching the E vector any arbitrary direction. There is no y component along, no x component along. So, there is both components are non-zero. So, this is a very interesting solution. So, let us try to understand this. So, E x, these two equation is 0, and in the previous case we consider either E x is equal to 0 or E y is equal to 0. Now, we consider both are non-zero. That means, I am launching an electric field in the plane of x and y as the figure suggests, and this component E x component is now written by E x E 0 some amplitude into sin theta, and E y component is now written E 0 some cos theta. So, these two components are now not equal to 0. So, they both are non-zero. If that is the case, then we will find that the refractive index here is n x and the refractive index here is root over of k y. Here it is root over of k x. E is still propagating along z direction. So, what will happen here? That is the interesting thing. Now, these things will, the polarization of E, is it conserved here? The answer is no, because it will not going to conserve. In the previous case it was conserved, because when I launch the electric field only along x direction, it will experiencing only one refractive index, and that is root over of k x. Another condition was, if I launch the electric field along y direction, it will be experiencing only one refractive index, and that refractive index was root over of k y. But here what happened, the two component of the electric field will be experiencing the refractive index root over of k x and root over of k y. That means, two component will experiencing the refractive index, and these two refractive index are different. What is the consequence of that? The consequence is, or rather the consequences are that the velocity of this particular component will be c divided by root over of k x, because we know that the velocity is in a medium is c divided by the refractive index. So, it will be c divided by k x, and the velocity of these components y component will be c divided by root over of k y. So, the velocity of the two electric field component is now will not be same, it will be different, and if this is the case, then what happened, let us see. So, what happened, that the one component will travel with the faster speed and another component will be traveling traveling with a lesser speed. So, if I write my total electric field, at z equal to 0, it will be the component x component E 0 cos theta multiplied by unit vector s, it will be E y sin theta y component multiplied by the unit vector y, and then e to the power I minus omega t, this is the phase associated with the field. Now, what happened if I increase the distance? That means, now the electric field is moving along z direction, because k is along z direction. So, what happened, that the one component x component, there will be a refractive index, and this refractive index or the velocity is c by root over of k x. So, if I write the corresponding phase, this phase will be I of omega c root over. So, we know that the phase is k z minus omega t. Now, here the value of k will be omega c then multiplied by n x z minus omega t, k will be replaced by omega c multiplied by n x. I write n x because the refractive index along this is different. If I now replace n x by root over of k x, then here we have the term omega c root over of k x, which is nothing but the propagation constant along x direction z minus omega t. In the similar way, for y I will have another term, and this is this exactly the same term, but root over, in place of root over k x I have root over of k y. So, that means, if I launch the electric field any arbitrary direction, but in x z x y plane, that has to be, because E z component will always be 0 when I launch the electric field k along z direction, then E is perpendicular to the k, but we find that for arbitrary orientation, the polarization of the system, polarization of the electric field will not remain conserved. That means, the polarization will be changed, and why it is that? Because the component of E x and the component of E y of the launched electric field will be experiencing two different refractive index. So, these two different refractive indices now appearing in this equation in terms of k or the phase. So, the phase will be different for these two components, and once the phase is different for these two components, so this phase mismatch leads to the non conservation of the polarization. So, polarization of the this E vector is now will be changing. So, there will be some change in the polarization, the orientation on all these things will be changing once these things will move at different speed, the y and x component. Okay, so, one important thing we learned, that here many things are there, that if I launch the electric field along k along z direction, that is this, and as shown in this figure, there are three possibilities, three solution. One is if I launch the electric field along x direction and along y direction, these two are so called trivial solution, and we find there is no change of polarization. But there is another possibility is that I launch E in arbitrary direction in x y plane. In that case, the E x and E y both are non-zero, these components are both non-zero. If that is the case, we find that they will be travelling at two different speeds, and as a result what happened, that the polarization of the state of the electric field will be not remain conserved. So, we will have a system where the polarization will going to change. Okay, now go back to our slides and then find another condition. This is a very interesting condition, and we will try to discuss these issues also. So, what happened here in the previous case, so far we are deal with the orientation of the electric field under the condition that k is launched along z direction. So, launching direction of k was remain same. So, there was no change in the direction of k. If the k was in z direction, we find that E, there will be the value of E, and this E field was always perpendicular to the k. That means, even if I launch the electric field in an anisotropic system where the k vector and E vector are not supposed to be perpendicular to each other, but here if I launched k along z direction, they are indeed perpendicular. However, their polarization state will not remain same if E is launched in any arbitrary direction like this, as shown in the previous slide. But now what we will do, we will completely change the orientation of the k vector. That means, electric field is now moving in different direction, and this different direction is in, as the heading suggests, it should be along x z plane. For the simplicity, let us put y along x z plane. If it is along x z plane, but not in z direction, it will be any arbitrary direction, and then the row vectors, the row values, rho x, rho y, rho z values will have the direction cosines rather will have this. So, the rho x will be sin phi, the rho y will be 0, and the rho z will be cos phi. So, if I put if I put the vector component here and here, if I put the vector components, then I will have this value is mod of k multiplied by cos. So, mod of k was omega c, omega divided by c multiplied by n, and the rest value was rho z, and rho z is cos phi. In the similar way, here rho z is sin phi, and rho x is 0 because there is no component along y direction. So, this is the case. Now, it is interesting because rho x, rho y, rho z, previously there was two 0 values, and that was rho x was 0 and rho y was 0 and rho z was 1, but here we have value of rho x which is non-zero, value of rho y, value of rho z which is non-zero, only the value of rho x is 0. So, it will also modify the equation, and that 3 equation we derive. So, let us check what kind of modification it will produce. So, okay, this is the total picture right now. This is the total picture. So, now my rho x, rho y, rho z is this. If I put this rho x, rho y, rho z, these 3 mother equation, this is the most general equation of rho x, k x and k y, then what happened, that these values now replaced. Now, rho x will be replaced, rho x square rather will be replaced by sin phi. When I replace this as a sin phi, so 1 minus 1 plus sin phi, it will be cos square phi, sin square phi plus cos square phi is 1. So, I am using this. So, sin square phi plus cos square phi is equal to 1. This value if I take minus common, then 1 minus sine square phi. So, 1 minus sine square phi is cos square phi. So, that is why it is written as minus of cos square phi. Then rho x rho y and rho x rho z. Rho x rho y is 0 because rho y is 0. Rho x rho z is sin phi cos phi, and then I have Z. Next equation, rho y is equal to 0. If rho y is equal to 0, if I put rho y here 0 and if I put rho y here 0, so these two components will not be there, and rho y again if I put 0, so I will have one equation E y is this. And finally, the last equation, again I will put rho x rho y whatever the value we have. So, rho x rho z and this quantity and this quantity, if I put these things, so I will have sin phi cos phi and this sin square phi. So, I have 3 modified equation when I put rho, and this modified equation can leads to some kind of solution, a general kind of solution. So, let us try to find out what kind of solutions we will have. Okay. So, first solution, what will be the first solution? First solution, these are the 3 equations. This is interesting, this is very interesting, that I have 3 equations in my hand and try to find out the solution, try to find out the value of E x, E y and E z. So, what here the special thing, k is not along z direction, k is having k is in different direction having an angle phi, and then what we will do, we try to find out the solution. The first solution here we are assuming is, let us put k x, k z both 0, E x, E z both 0. If E x and E z both 0, then this equation and this equation are consistent, because if I put E x here 0, E y is 0, then this things is 0. So, right hand side is 0, left hand side is 0, no problem with that. Here also in this equation, if I put E x equal to 0 and E z equal to 0, I have left hand side is equal to 0, which is right hand side. So, these two equations will satisfy with the solution E x equal to 0 and E z equal to 0. But another equation is here in our hand, and we assume that E y is not equal to 0, because if E y is 0, then these are the trivial solution, all are 0. So, 0 left hand side will be equal to 0 right hand side. So, there is I mean there is no solution we have. So, now for these solutions, these special solutions, we have only one equation in our hand, and that equation is E y multiplied by k y divided by n square minus 1 is equal to 0. This is the equation I have. So, from this equation, if E y is not equal to 0, that means k y, like the previous case, big k y rather, sorry. So, let me erase this. So, big k y will be equal to n square. So, that means refractive index along y direction is root over of k y. This is the refractive index along this direction. So, if I look this solution carefully, this E is along y direction now, because this component and these components are not there. If that is the case, then what happened? This is now experiencing, this component will now going to experience the refractive index which is root over of k y, that is one issue. Second very important thing, even though I am launching the k not in z direction, but any arbitrary direction, the electric field along y direction will still be perpendicular to k vector. That means, I am launching the k vector along z direction and we find that electric field along y and E is there, which is perpendicular to the k vector in anisotropic medium, which is normally not the case. But here we find that even if I launch the electric field in some different direction, which is in x and z plane, but not in k direction, the perpendicular direction, along perpendicular direction, the electric field, the solution can be there, the electric field can be in y direction and it will be experiencing a refractive index k y and it will propagate without any kind of problem. That means, the polarization will remain conserved and it will propagate without any problem. That is one issue. Second thing is that k and E, they are perpendicular to each other even in this case. So, in anisotropic system, it is not necessarily that always that k and E will be not, this is the most general case that they are not perpendicular to each other, but some special cases like this, they may be perpendicular to each other. So, this is the thing so far we have done, but the most interesting thing we will come in the next class, that what happened if there is no field here. So, electric field is along the x and y direction. If the electric field along x and y direction, what happened, because this is the most interesting thing here, and then we find that they are not following the case. So, this is the problem that we are going to solve in the next class. So, just I am giving you the hint or the introduction of the problem. The problem suggests that in the previous case the solution was E y was not equal to 0, but E x and E z was 0. Now, I just invert the solution. That means, now I consider that E y is 0, but E x and E z is not equal to 0. In this, under this condition, now we have two equation in my hand, because other equation will vanish automatically. E y equation will not be there because E y is this. So, now we need to solve these two equation under the condition E x and E y is both not 0. That means, E x and E z components are there, but E y component is not there. If I try to understand with this figure, I am launching the electric field along this direction, which is x z plane, and E is also in x z plane, because E x component and E x and E z, these two components are non-zero. That means, it has to be somewhere in this plane. This is maybe one orientation of E, but it has to be in that particular plane. So, with this note, I would like to say that in the next class we will solve this very interesting problem and try to find out that how the E and k vector, which was so far perpendicular, is really in the for solution 2 will be perpendicular or not. If it is not perpendicular, then how to measure the angle between these two. That is the most important thing, and that is the thing we are doing, that to find out the angles between whatever the vectors are there in anisotropic system, because if we know the angle between these two, we know in which direction they are flowing. That is one issue. Second issue, how this angle is related to the refractive index. So, if the refractive index is given to you, you can calculate the angle, the walk-off angle, the angle between the vector k and s or the vector d and e. How to calculate that, we will find out in the next class. So, with that note, so let me conclude here. So, see you in the next class. Thank you for your attention.